Hello, this is your instructor, Tom Perepsky again, and this is the last part of Module 3, Part 4. We're going to look at association between two variables. We're going to look at something called the covariance and something called the correlation coefficient. As we've seen, a single variable has a variance to it. Well, if we have two variables, they have something called a covariance between them. And the covariance is going to be a measure of linear or straight line association between two variables. An upward sloping relationship will tend to give us a positive covariance, and a downward or negatively sloped relationship will give us a negative covariance. I'm going to give you formulas for the covariances, although as we'll see in a minute, we might not actually need to use them in the calculation. I'm going to give you an alternative way of doing the correlation coefficient in a moment. Again, we're going to give you two different formulas for a sample and a population. If the data is if we have two variables, a sample of two variables, we use the notation SXY to stand for the sample covariance between X and Y. You're going to take the deviations around the X variable multiplied by the corresponding deviations around the Y variable, add them up, divide by n minus 1. If your data is populations, or you're treating it as a population, we have two variables, X and Y again. Now the means, of course, will be the population means. Again, we take each deviation around the X variable times its corresponding Y variable. Remember here we have two variables that are in a sense ordered pairs. For example, if we took a sample of 10 people and we got each person's height and weight, and we wanted to do the covariance between heights and weights. So for each person, you're going to have a height variable and you're going to have a weight variable. We'll call those X and Y. It doesn't matter with covariance and correlation which one you call X and which one you call Y. Now again, calculating a covariance can be a little bit tedious, especially if the means are fractional. Then calculating those deviations can be somewhat difficult. This is a graph which just kind of explains why does the covariance give us a linear association. Take our standard XY plane between our two variables. I'm going to put lines where the mean of the Y's occurs and where the mean of the X's occurs, wherever those 2 points happen to be. If you have an upward sloping relationship, notice you're going to get a lot of data in the first quadrant and the third quadrant. These lines have divided this into two quadrants. I've repeated the covariance formula over here so we can take a look at something. Notice that all the data in this first quadrant, the X coordinate would outweigh or be greater than the mean of the X's. So Xi minus X bar would be a positive number. The Y coordinate, this distance, would also outweigh the mean of the Y's. So in this numerator, Y minus Y bar would be positive. So if you look at the formula, you'll see that for all the points in the first quadrant, Xi minus X bar is positive, Yi minus Y bar is positive, and that's going to give you a positive covariance. Similarly, down in quadrant 3, the X coordinate is less than the mean, and the Y coordinate is less than its mean. So now, both of these deviations would be negative. And of course, if you remember your math, a negative times a negative is a positive. The moral of the story is that when you've got most of your data in quadrants 1 and 3, this numerator is going to be a positive number, and that's why you will get a positive covariance. Just the opposite for a downward sloping relationship. Then you would get a lot of data in quadrants 2 and 4, and you can show that the numerator in this case would be a negative number. Now there is a problem with the covariance, and a reason why I don't stress its use too much. It's very sensitive to the units of measurement. Go back to the example I just talked about. Supposing I took a sample of people in the classroom and I looked at their height and their weight, and I wanted to measure the covariance. Well, I would get a different value if I measured weight in pounds versus weight in ounces, or height in feet versus height in inches. The value of the covariance would change. We generally prefer statistics that remain the same regardless of the units of measurement. And fortunately, we have one. We can go from the covariance to what's called the correlation coefficient. A correlation coefficient also is a measure of linear association between two variables. It can be shown mathematically. The correlation coefficient ranges from -1 to +1. The only way you would get a value of +1 is if all of your points lie exactly on an upward sloping line. The only way you'd get a correlation of -1 is all of your points lie on a downward sloping line. Here, for example, all the points on an upward sloping line, we'd have a correlation of +1. And a downward sloping line, we'd have a correlation of -1. In general, then, the closer a correlation is to 1 or -1, it tends to indicate a stronger correlation. Correlations close to 0 imply no linear relationship. There could still be a nonlinear relationship, but not necessarily linear. Now, if we want to calculate a correlation coefficient, there's a couple ways we could do it. I'm going to stress one of them over the other, but then we'll also show you how to do this on your calculator. First, our formulas again will differentiate a population correlation coefficient from a sample correlation coefficient. This is the Greek letter rho. Rho xy stands for the population correlation coefficient. One way to calculate it is you take the population covariance that we looked at a minute ago and divide it by the product of the two standard deviations, sigma x and sigma y. You could do something similarly for a sample of data, except we're going to call it Rxy. Rxy stands for the correlation coefficient, the sample correlation coefficient, or more generally just called R. Again, we would take the sample covariance over the product of the sample standard deviations. Now, if you plug the formula in for the covariance and the standard deviations and play around with it algebraically, you can get what I'm going to call a computational formula. And here's our computational formula. And we're just going to look at this for a sample correlation coefficient. I know the formula looks kind of big and ugly, but don't let it scare you. As I said, we'll show you a nice shortcut in a minute for those of you with TI-83 or 84s. We'll show you how to do this on your calculator. But if you want to do it by hand, if you just look at all the sums that you need, you have two variables in doing a correlation, x and y. And again, as I said a minute ago, it doesn't matter which one you call x and which one you call y. Just keep it consistent throughout the problem. You're going to need to sum your x's, sum your y's, multiply those together and divide by n here in this term. Summation xi yi basically means multiply each value of x times its corresponding y value. In the denominator, we have these two square root terms. One of them involves the x variable, and one of them involves the y variable. You're going to need to square the x's and add them up to get this term right here. Similarly, over here, you're going to need to square the y's and add them up. Here we just have summation x. Take the quantity of that squared and divide that term by n, and similarly over here for the y variable. Let's do an example, and if you have to do a correlation by hand, be careful with the calculations. There's lots of places for making errors. Oh, and don't forget in the denominator, this is a square root and another square root of these entire terms. So let's do an example. First, let me just make up two sets of numbers without any particular context to them. Let's say we've got x values here of 5, 3, 4, 7, 8, and corresponding y values of 8, 2, 3, 9, 10. Sum the x's, they add up to 27. Sum the y's, they add up to 32. Multiply across. 5 times 8 is 40, 3 times 2 is 6, and so on. Add those up, and that'll give you summation xy, the sum of the, what I call the cross product term between x and y. Square all of the x's. Come over to this column and take all those numbers and square them. 5 squared is 25, 3 squared is 9, and so on. They add up to 163. And then do the same thing for the y's. Square them and add them up. And you'll get 258. Now let's just plug all the numbers in the formula. And again, if you carefully go through the calculations, step by step, you should come up with a correlation of 0.933. Notice that's a pretty strong positive correlation. As we saw a minute ago, the correlation coefficient only varies from -1 to +1, so 0.933 is a very high positive correlation. Let's do one more example, except this time we'll give a context to the problem. Suppose we were interested in the relationship between a student's grade on the final exam and the hours they spent studying in the 3 days prior to the final. A sample of 6 students from last semester gave the following data. So suppose we took a sample of 6 students and we have how many hours they studied and what their grade on the final exam was. So one student who studied 10 hours got a grade of 90, somebody who studied 5 hours got a grade of 70, etc. Let's calculate the correlation coefficient again and interpret our results. Again, like we did a minute ago, I'm going to let y be the grades, x be the hours of study, and let's do all of our intermediate summations. Summation y is 450, summation x is 42. Multiply across xy and you'll get a sum of 3400. Square the x's and add them up and you'll get 346. Square the y's and add them up and you will get the last term there of 36,350. And now let's plug everything in our formula again. Again, be careful if you're doing this by hand for calculation errors. Plug all the numbers in, slowly start to get the results. You should end up with a correlation of 0.866. Again, we have a pretty strong positive correlation, remembering that the correlation coefficient can't be higher than +1. Later in the course, we're going to do something similar to correlation. In a future module, we'll be doing what's called simple linear regression, where we actually hypothesize that a variable y is specifically a function of a variable x. And in that case, it'll matter which variable we call y and which variable we call x. And instead of just calculating a correlation between the two, we're going to fit a line through the data, called the simple regression line. But that will come later on. Okay, now let's try to make it a little bit easier for you. Can you do this on a calculator? If you have a TI-83 or 84, the correlation coefficient doesn't have its own separate program on a TI-84, but it is contained in other programs. First, you might have to turn diagnostics on your calculator. To do that, press the second level button and hit the number 0 to access the catalog. Scroll down until you find what's called Diagnostics On and hit your Enter key twice. You should only have to do this once. Once it's on, it should stay on. Put the two variables in lists, as we've talked about in earlier modules. Let's say L1 and L2. Again, as I've said before, it doesn't matter here which variable is your x variable and which one is your y variable. Press the Stat button, scroll over to Calc, and scroll down till you find what's called linear regression. That's an abbreviation for linear regression AX plus B. Hit your Enter key, and then the calculator wants to know where the two variables are. So if you put your data in L1 and L2, hit the second level button and the number 1 to get to L1, hit the second level button and the number 2 to get to L2. Don't forget a comma between them. Hit enter. There'll be some other results there that you don't need to worry about for right now, but you'll see something called R, which is the correlation coefficient that we just calculated. You'll also see the square of R, which is something called the coefficient of determination, which we will get to in a later module. Let me show you one other way to do this before we end this section. Let's go to Excel. A lot of you probably already have familiarity with Excel. Excel has a lot of statistical functions in it. Here I've just repeated our data on the two variables, put one variable in one column and one variable in another column. So I've got the grades and the hours of study. If you click the little F sub X button here, the Insert Function button, and if you select here the statistical category, you'll find all sorts of statistics that we can calculate. If you scroll down a bit, you'll see one abbreviated CORREL, which is short for correlation. Click OK. Let's move this over. And now Excel wants you to tell it where the data is. Where's your two variables? So array 1, when the cursor here is highlighted, you can just go to the first variable, click and hold your mouse, and it will tell the computer where your first variable is located, A1 through A6. Click into the second variable and do the same thing with the second variable. Hold your mouse down and drag through it. And there's the correlation coefficient right there. Might be hard to see on the screen, but 0.866, which we just had done by hand. A lot easier, a lot quicker than doing it by hand. And that is the end of Module 3. And next we'll move to Module 4, where we cover probability.